This from the definition of entropy, that is Q1 upon T1 is the S1. It is the entropy gain by sink, and Q2 upon T2 is S2, entropy loses by source. So the source loses this entropy, and S1 is the entropy gained by the sink. So the net entropy change, as we know that net entropy change is S2 minus S1, and which is greater than 0, which is positive. So for reversible process we can write, for reversible process, this Q1 upon T1 is equal to, for reversible process, Q1 upon T1 equal to Q2 upon T2. So both having same value, heat gain heat gain by the sink as well as entropy loses by the source. So S2 minus S1, these remain same. So for reversible process, delta S is the summation of the entropy changes in the different processes, so that becomes equal to 0. So entropy change for reversible process is 0, and for irreversible process, as we know that for irreversible process, the process is always accompanied by increase in entropy. So net entropy change, if we calculate net entropy change, then here delta S is the summation of the entropy changes in different steps, and which is greater than 0. Greater than 0 means there is a positive entropy change. So entropy increases in the irreversible process. So from this we can write that entropy always increases in irreversible process. So entropy always increases in the irreversible process. So this is the entropy change in irreversible cycle. In irreversible cycle, there is always increase in entropy. So irreversible process is always associated with increase in entropy. So the next point that we which is related to energy that we have to study here, that point is a free energy and work function. Free energy and work function, or sometimes this free energy is called as Gibbs function, which is indicated by symbol G, and work function is sometimes called the Helmholtz function, which is indicated by symbol A. So Gibbs function, Helmholtz function. Now see here energy, as we know that the energy is used to perform work, but not all energy, as the first law says that energy is converted from one form into another form by performing some work. It may be converted into some another form, but not all the energy is converted into work. So energy which is converted into useful work, means energy which is utilized to do useful work is one type of energy, and another energy which is not useful to perform work, or which is not utilized to perform useful work. So energy is of now two types, which is utilized for performing useful work and not useful for performing useful work. So these are two types of energy. The energy which is utilized to perform useful work is the available form of energy, and this is the unavailable form of energy, which is not utilized to perform the useful work. So that energy is the unavailable energy. So how can we state total energy? So total energy is the summation of isothermally available energy and isothermally unavailable energy. So these are two forms of energy, available energy and unavailable energy, and total energy is the summation of available energy as well as unavailable energy. So total energy is here. Now we have to study about the isothermally available energy, and this available energy is in the two forms here, Gibbs function and Helmholtz function. So these are work function. This available energy is converted into work. Okay. So now see these two terms, that is Gibbs function, G is equal to, it is defined by, this is a form of energy. Enthalpy, as we know that it is a form of energy. Now at constant temperature some work is done. We know that work done in irreversible process, work done is always accompanied by increase in entropy. So work done is here, so in the form of entropy change. Okay, so G is equal to H minus Ts. So this is available form of energy and this is work done. So work is done from this available form of energy, and if enthalpy is the form of energy, then that function G is called as Gibbs function, or it is a form of free energy. So what is this Helmholtz function? Helmholtz function is defined by, here available form of energy is internal energy. Internal energy is the available form of energy. Now this internal energy from which work is done in the form of increasing entropy at constant temperature. So isothermally available energy, internal energy from which work is done, and that is nothing but Helmholtz function, or we say work function. Okay, work function and Helmholtz function. Now it can be also modified in the form of work function also. G is equal to H. We know that H is equal to E plus PV, enthalpy. From the definition of enthalpy, mathematical expression of enthalpy, we can write H is equal to E plus PV. Now H is equal to E plus PV. If you write here E plus PV minus Ts, this equation we can write. Now if we rearrange this equation, E minus Ts plus PV, and if we look at the definition of the work function, that A is equal to E minus Ts, so it is a work function A. So we can replace this term here. So in terms of work function, we can write this Gibbs function A plus PV. So it is another form. We can write free energy or work function, free energy or Gibbs function in this way. So this is Gibbs function and this is Helmholtz function. Okay, let's see the physical significance of these two work functions. These two functions, these two available forms of energy. So physical significance, let's see first physical significance of the work function. So physical significance of work function. Physical significance of work function represented by symbol A. Now suppose that A1 is the work function or isothermally available energy of state 1. So A1 is equal to E1 minus Ts1. Okay, write it equation number 1. Now suppose A2 is the work function of state second, it is represented by E2 minus TS2, equation number 2. By subtracting equation 2 from 1, we can write A2 minus A1 equal to, we write E2 minus E1 minus TS2 minus S1. TS2 minus S1. So we can write delta A is equal to, here E2 minus E1, that is a state function. So delta E is a state function which depends on initial and final state. Here entropy minus T, entropy S2 minus S1. Entropy is also state function which depends on initial and final state of the system. So it is represented by delta. And here similarly it depends on two functions, internal energy as well as this entropy. So both are state function, as this work function is also a state function. It depends on initial and final state of system and not the path followed. So delta E is equal to delta E minus T delta ES. Now look at the definition of change in entropy. We can represent, see the change in entropy, delta S is equal to Q reversible upon T. Q reversible upon T. So Q reversible is equal to T into delta S. If we rearrange this equation, then Q reversible is equal to T delta S. If we replace this term T delta S by Q reversible, we can write delta A is equal to delta E minus Q reversible. Okay. From first law of thermodynamics, let's see. From first law, what is its mathematical expression? From first law, mathematical expression says that Q is equal to delta E plus W, or in another form we can write delta E is equal to Q minus W. Okay, now I can write here Q capital. So the first law, from first law mathematical expression, Q Q reversible equal to delta E minus W. So this is it is mathematical form of the first law of thermodynamics. So we have to arrange this equation in this form, delta E minus Q reversible. So if we take delta E here, then Q reversible minus delta E equal to minus delta W. And if we change the signs, and for expansion type of work, we can write delta E is equal to Q minus W for expansion type of work. Now we have to consider here expansion type of work, delta E is equal to Q minus W. Now if we have to change this form in this way, delta E minus Q reversible. So delta E minus Q reversible equal to minus W. So forget about this compression type of work. Here for expansion type of work, we can write delta E minus Q reversible equal to minus W. So delta A is equal to, this term is replaced by minus W, or we can write this equation W is equal to minus delta A. So this equation gives the significance of this work function. What is the significance here? Decrease in work function is the magnitude of work done. So maximum decrease in maximum decrease in the work function, there will be maximum work done. So it gives the significance that decrease in work function gives the maximum work. So it is a measure of maximum work. Decrease in work function is a measure of maximum work. Measure of maximum work. It is a measure of maximum work. So this is about physical significance of work function. Work function, from work function we can calculate maximum work. Okay, so see the physical significance of free energy. Physical significance of free energy. What is the physical significance of free energy? Free energy. Now we can represent two equations for free energy for initial state and final state. Suppose that G1 H1 minus TS1 and G2 represent the free energy of second state H2 minus TS2. Second state H2 minus TS2. So from the if we subtract the quotient second from 1, then G2 minus G1 equal to H2 minus TS2 minus H1 minus TS1. Okay, so G2 minus G1 is a delta G. Is it delta G? And here we can separate H2 minus H1 minus T is a common here, S2 minus S1. So we can write delta G, change in free energy is equal to H2 minus H1 is the delta H minus T common, and H2 minus S1 is a delta S, T delta S. Okay, now we know that delta H represents enthalpy and delta H represents enthalpy. As we know from the definition of delta H, what is the definition? Delta E plus P delta V. Enthalpy change is given by this equation. Delta H is equal to delta E plus P delta V. Now delta G, if we replace this delta H, delta E plus P delta V minus P delta S, and somewhat rearrangement gives delta E minus P delta S plus P delta V. We know that this term delta E minus P delta S is what? It represents the change in work function, delta A. So delta G, as we know that, what is delta A? Delta A is equal to delta E minus P delta S. So we have to replace this term here. So now delta G can be written here, delta E minus P delta S is a delta A plus P delta V. And from the significance of work function we can write what is delta A is equal to minus W. From significance, the decrease in work function is nothing but the maximum work done. From this we can write delta is equal to minus W. So delta G is equal to, here we can replace this minus W plus P delta V, and if this whole equation is multiplied by negative sign, we can write minus delta G is equal to W minus P delta V. P delta V. Here it is work done of another type. Here it is work done of pressure volume type. So it represents net work done. So this both are work quantities. So net work done minus delta G represents net work done, which is W minus P delta V. From this work, how much of pressure volume type of work is done. So it represents net work done. So minus delta G represents net work done. So this is physical significance of this free energy. So decrease in free energies gives net work done. Decrease in free energy gives net work done. So this is the physical significance of free energy. And last one we saw the physical significance of work function. Okay, so this is about free energy and work function. Now the next point that we have to study is the variation of entropy with temperature. variation of entropy with temperature.